Okay, so now let's move on to our last bit here with dividing rational functions. Okay, so you've already seen the very first step on all these seems to be that we're going to factor everything. Okay, so let's factor all of these actually polynomials. So this one right here, this last one is just a binomial, but nonetheless we're going to factor it. Okay, so we have x plus 1, x minus 1, because it's a difference of squares. On the bottom piece, we always want to do GCF first if we can, just like we did back in the day when we were factoring with quadratics. So GCF out a 2x so that you have x minus 3 left over. Okay, so all I did was take out a 2x from both of them because they both had the greatest thing in common was a 2x. So the leftover scraps inside would be x minus 3. So we have x minus 3, we have 2x. Okay, so now this is different. We have dividing. Okay, and I'll get to that here in just a bit. Let's go ahead and factor the other two over here on the left side. So we have up top, we have x plus 4, x plus 1. And on the bottom, it looks like we have x plus 4, x minus 3. Okay, so the big thing about dividing fractions, multiplying fractions is easy. You could just multiply straight across and straight across. But again, you always want to reduce first, okay? Reduce first before you start multiplying across everything that was left over, just like we did over here at the bottom. Reduce first before you multiply straight across all those pieces that are left over, okay? So with division, we're just going to make it a multiplication problem by understanding that when we're dividing by a fraction, it's the same as multiplying by its reciprocal. So if I had 5 divided by 2, it's the same as 5 times, because we're going to change this to multiplication, and we're going to flip this. So you learned this way back in 5th grade. If not, it's called keep, change, flip. So we kept the 5 as 5. We changed the division to a multiplication. And we're going to flip or get the reciprocal of what 2 is. Well, 2 is technically 2 over 1. And if I did the reciprocal, I'm just going to flip-flop the 1 to go up in the numerator and the 2 to go up or down into the denominator. So now I have understood 5 over 1, which if I multiplied straight across, just like I did, and I was showing you right here, if I multiply straight across, I would get 5 times 1 is 5, and on the bottom, I'd get 1 times 2. It's just going to be 2. So it's 5 halves. Okay? So when you're dividing by something, it's the same as multiplying by its reciprocal. So that's what we're going to do here. We're going to take all of this, whoa, a little bit too much, right here, and we're going to copy this, and I'm going to show you the keep, change, flip. So I'm going to change this to a multiplication, because it was division, and now I'm going to flip-flop. This denominator is going to go up here, and the numerator is going to move down. So we have x plus 1 in the bottom, x minus 1, and then 2x, x minus 3. Okay, now let me color coordinate it. Keep, we kept this. Okay, change, we changed this. And then finally, flip, we flipped this piece right here. And now is when we can start reducing like we've done before. Okay, we're looking at this like a multiplication piece. This is all glued together still as one huge fraction that you're basically going to treat as one big fraction with one numerator, one denominator, where you can start cancel reducing, okay? So let me go ahead and write that as one huge fraction. Now let's cancel reduce. I have an x minus 3 that will go with x minus 3. I have an x plus 1 that'll cancel with this x plus 1. I have an x plus 4 that'll cancel with this x plus 4. So the only pieces that are left are here in gray of 2x and x minus 1. Please, 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 do not cancel this x and this x, because 1 down here is a part of a binomial because it has this subtraction piece to it, where this one has multiplication. So if this has multiplication and this has like an addition slash subtraction, you cannot, whoops, that's not how you spell subtraction. So you cannot abbreviate it. You cannot cancel those because they both have to be multiplication and multiplication. So I either need this just to be an x on the bottom, not with x minus 1, or I need a full x minus 1 up here so that it could cancel with the entire thing. Okay, but because we don't have that, we are not going to reduce. So what's left over to just go ahead and multiply is 2x. And what's left over to multiply on the bottom is just this x minus 1 is all by itself. So this is our most reduced, simplest form. The restrictions will happen, okay? They will happen over here in this factored piece. So we have a -4, we have a +3, we have a -1, and we also have a 1, okay? But get this, we also have to look at the original one too. So not only do we look at the flipped one, where it was a new denominator because of this keep, change, flip, we also have to look at the original. We have to look at any and all pieces, basically, where the x was in the denominator that would make it be undefined because it would be dividing by 0. So let's go ahead and list out this one right here. So x cannot equal -4, x cannot equal 3, x cannot equal -1, and I'm getting it from all of these right here, and x cannot equal a +1. Then when we come over here, we still see, well, -4, that's already been taken care of, 3, that's already been taken care of. Ooh, but there's this other one here that's new, x cannot equal 0. And then here, x cannot equal 3. That's already been taken care of. Okay, so all of these would be the restrictions. Make sure that you understand that it's not only from the new flipped factored piece, but the original factored piece as well. Our last example is right here. So your community is building a park. It wants to fence in a place or a play space for toddlers. It wants the maximum area for this given amount of fencing, for a given amount of fencing. So which shape, a square, a circle, provides the most efficient use of the fencing? Okay, so first of all, notice that we don't have any numbers that are given to us. So what makes this a little bit difficult is the fact that we have just variables that are going to show into place. So if I have a square versus a circle, we're going to look at what are the areas going to be. Okay, so square and circle. That's what we're going to be working with first. And it says a given amount of fencing. Okay, so a given amount of fencing is talking about the perimeter. So if for a square, we're going to say that the perimeter is equal to 4 times the side, or s plus s plus s plus s. Same thing as 4 times the side. And we're going to say the perimeter for a circle is the circumference, so 2 pi r. Okay, and what we're trying to do is we're trying to maximize the area. So the area here for a square is going to be, area is equal to side squared, and the area for a circle is pi r squared. Okay, and now what we're going to do is we're going to see how we can substitute certain pieces as far as figuring out how to maximize the area per se. Okay, so let's look at a ratio that exists. Okay, let's look at, let's look at it this way. I have 2 equations on both of them already right now. So if I wanted to compare their areas, what I'm really doing is I'm trying to make sure that these variables are pretty much kind of like the same, if you will. Okay, so if I looked at this and I wanted to do it in terms of P, because it's all about that perimeter, that amount of fencing that was in fact given, I'm going to go ahead and use the perimeter equations to solve for S. Okay, I'm going to get S by itself for this first one. So it would be like P over 4 is S. And then I'm going to get R by itself over here. by saying P divided by 2 pi is R. So what I got is S in terms of P and R in terms of P. And the reason why I did that is over here where I would see a normal S in the equation, I'm now going to put this P. So I'm going to substitute P over 4 where S used to be. So it's S squared is equal to A. Notice how I use these two equations to make that happen. So then I'll come over here, and where R is all by itself, I'm now going to come over here in this equation. I'm going to substitute all of this. So it'll be like this. It'll say area is equal to pi times R squared. And we learned that R, because of this other equation with perimeter or circumference, is P over 2 pi. So now I have area with area, and it's with the same variable. Now I can compare apples to apples and oranges to oranges, if you will. Okay, I can compare the same pieces. So this will become, if I were to like simplify it out and see what's going on as far as like its area maxed, I could say that area is going to be P squared over 16. And over here, I could say this is P squared over 4 pi squared, because I applied this 2 to every little piece in this monomial. And then I still have this pi out here is equal to the area. So right now, this is what's going on. If I were to reduce the things that it has in common now, I could reduce this. I have 2 pi's on the bottom because pi squared is like pi, and another pi. And right here I have just 1 pi up top where there's that cancellation form of 1, which only 1 will be left over on the bottom. So we'll take this off and it'll look something like this. Okay, so I have that divided by 16 and this divided by 4 pi, if you will. Okay, and 4 pi is like less than 16. Okay, so 4 pi is like 3.14 times 4. So it's like 12 and some change, if you will. Okay, so if I have P squared divided by a big number, this will equal a very small answer. But if I had P squared divided by a smaller number, this would equal a bigger answer. So again, when that denominator is big and you're dividing by a big number, it's going to come out to a small number. As far as like the entire thing here is going to be a small number. But if I had the denominator as a small or a smaller piece, if you will, the way I did over here, I had like 12, okay, then it will yield a bigger answer as far as the whole thing is concerned. Okay, so what's going to be the bigger piece? The bigger piece is going to be this area of the circle is going to be bigger. Okay, so we could say that P squared over 4 pi is bigger than P squared over 16. And if you were to actually like give it examples and put numbers and show what those values would be, you can see in the written key that it does show an example of that way, and it does verify that the circle would in fact be what maximizes that area.